Right, thank you. I'm hoping the microphone is working so that everyone can hear me. Otherwise, please let me know to the online audience. And also, I wanted to remind you that if you have any questions during the talk, please feel free to interrupt me, or if you're online, unmute yourself and ask your question. I wonder how I can get these Zoom controls to disappear, but perhaps that's not important. Okay, well, so the topic of the talk is going to be convection, and we've heard about convection a couple of times in this workshop, and we've mostly been hearing about boundary-driven convection in the Rayleigh-Bernard model. So that's just one flavor of convective motion, but convection is ubiquitous in nature. You see it at a small scale, you see it at a very large scale, and it can be driven by different physical phenomena. So boundary-driven convection driven by buoyancy is just one example, but if you go to the small scales, for example, drying paint, free surface flows, then instead of buoyancy, convection gets driven by thermal differences and surface tension. If you go to the other end of the spectrum, perhaps in astrophysics and geophysics, you have convection where the sources of heat doesn't come through the boundary, but comes from some internal reaction or chemical reaction and so on. So there's internal heating as opposed to boundary heating. So in today's talk, I would like to consider the internally heated case. And you can pose the same type of questions that we've heard about in this workshop before, and David gave us a nice introduction yesterday to an overview of Rayleigh-Bernard convections. And you can ask questions about heat transport, behavior of various quantities in these systems, and each one of these come with their different subtleties. So not everything can be boiled down to studying the Rayleigh-Bernard model. So in this talk, I want to consider an idealized model of internally heated convection where the heating is uniformly distributed in the domain. The fluid is in a horizontal layer bounded between two plates, which are at a distance d, but I'm using that distance to non-dimensionalize everything. So the depth of this non-dimensional layer is 1. And the motion of the fluid inside this layer is governed by the standard non-dimensional Boussinesq equation, but with two important differences from what we've seen before. One is the presence of a unit source on the right-hand side of the heat equation, which is this uniformly distributed source of heat. And it is unity because I've non-dimensionalized the temperature units using the heating rate in order to build my temperature scale. And as a consequence, the second difference is in the definition of this Rayleigh number, which I denote by R, as opposed to RA, which is the standard one, because it is a flux Rayleigh number, and it is defined using the dimensional magnitude Q of this uniform heating source. So the temperature scale here would be QH squared over kappa, I believe. So for boundary conditions, I've heard that Idris was worried about that. Of course, we need to equip these equations with boundary conditions. So everything that I will say today will be for non-slip velocity boundary conditions, but we have a choice of thermal conditions, and I will comment on that in the next slide. Irrespective of the choice of the thermal boundary conditions, the question that I would like to ask, and that many people have asked before me, is if you consider a function of the velocity or of the temperature, you can see how it evolves in time. And the question is, can we predict the space-time average of such a quantity, let's say any quantity phi of u and t being the temperature and u the velocity, and can we predict how it varies in terms of the governing parameter, which in this case are the Rayleigh number, or this flux Rayleigh number more precisely, the Prandtl number, which is the ratio of kinematic viscosity to diffusivity, and perhaps the aspect ratio of the domain. So horizontally, I'm assuming that everything is periodic with period gamma x in the x direction. And in the three-dimensional case, there will be a direction that goes into the slide. That would be the y. There would be an aspect ratio in that direction as well. So the question is, can we predict these space-time averages? And in terms of notation, I'm using angle brackets for volume averages and overbars for infinite time averages. And you could define these as lim sup as opposed to limits if you want things to be well defined. But I don't want to deal with these technicalities at this point. So this is the setup, and there are many quantities that one could consider. So one quantity that's been studied a lot in the past is the mean temperature. And by energy identities, this is the same as the thermal dissipation. And so if you know anything about Rayleigh-Bernard convection, then this mean temperature perhaps is behaving a little bit like 1 over a Nusselt number. This is an analogy that one could make to keep things in mind. And this is because it is related effectively to this thermal dissipation. And here you see that with different choices for the temperature boundary conditions, you can get slightly different, well, in this case, yeah, so slightly different results. So we don't know exactly how these quantities behave their behavior might depend on the initial condition, as David was explaining yesterday. But we could set up for bounds on these quantities that apply to every possible initial condition of the system. So for this mean temperature, you can have upper bounds that are uniform, that don't depend on any of the parameters, and they are determined effectively by the purely conductive state, where there is no flow and the temperature is just conducting out of the domain. In this IH1 case, where both of the boundaries are held at a constant temperature, which I'm going to set to 0 without loss of generality, then the heat is conducted, is flowing out of the domain, is being added in the domain uniformly, and it's being transported outwards by convection. In the bottom case, I'm going to call it IH3. I replace the bottom boundary with a isothermal boundary. Instead of that, we have an insulating boundary. So the flux of temperature, so the z derivative, z is the vertical coordinate here of the temperature, is 0. In this case, all of the heat must exit the domain through the top. And so that's why you get different conductive profiles and you get these different uniform upper bounds. More interestingly, you can look at the lower bounds on this mean temperature, which one might believe apply to these turbulent regimes or unstable periodic orbits or unstable fixed points. And these lower bounds depend on the Rayleigh number. So they decrease to 0. And if you fix a Prandtl number arbitrary but finite, then you discover that the mean temperature cannot decrease faster than Rayleigh to the -1/3, irrespective of the boundary conditions. And these bounds are uniformly in the Prandtl number. So the prefactors here are just absolute constants that one could track. If you decide to go at the infinite Prandtl number case, then you can do a little bit better. You can extract a little bit more information from the governing equation, and you can prove bounds that decrease more slowly. So they go as Rayleigh to the -1/4 up to logarithms. And these agree with heuristic predictions that have appeared quite recently in the literature and somehow mimic this Grossman-Lose theory that David was talking about yesterday. And these predictions say that if the Prandtl number is small, sufficiently small compared to the Rayleigh, then one expects the mean temperature to scale as Rayleigh to the -1/3, which is consistent with these lower bounds here that apply at low Prandtl number as well. And if the Prandtl number is large, and in particular infinity, then one expects the mean temperature to scale as Rayleigh to the -1/4. So all of these rigorous results that have been proven by Lou, Doering, and Busse, and then by Whitehead and Doering, actually agree with these phenomenological predictions. So the picture here is fairly complete. We kind of understand, we believe we kind of understand what's going on, and so there doesn't seem to be much room for improvement. But this is only one quantity that we could look at in this flow. There is a different quantity, and that's the mean vertical heat transport. So in this talk, W here is the vertical component of the velocity. T, of course, is the temperature. And so I'm going to look at the space-time average of WT, which in the Rayleigh-Bernard case can be related to the thermal dissipation. All of these quantities are related in Rayleigh-Bernard, but in the internally heated case, there is no a priori relationship. The only thing that we know from energy balances is that this mean heat transport is proportional to the viscous dissipation in the system. And in this case, the situation is much less complete. So all we know, at least all we knew until quite recently, were these uniform bounds that are the same in all of these 4 cases that I'm considering here on the slides. The 0 lower bound corresponds to the conductive state where there is no flow, so W is equal to 0, and so they are sharp. But this upper bound of 1/2 is essentially telling us that all of the energy gets transported by convection. And so it's not very interesting. And in particular, these bounds do not correspond to what one sees in simulation. So here I'm plotting some data from experiments that go back to 1972, 3D DNS, 2D DNS, some quite recent, various Prandtl numbers. So here are the symbols. The crosses are experiments, the squares are 3D DNS, and the circles are 2D DNS by various authors. The colors represent the Prandtl number. And so you see that as you increase this Rayleigh number for a fixed Prandtl number, this heat transport seems to increase somehow, and then perhaps approach a constant, but we're nowhere near being anywhere near 1/2, right? So these uniform bounds of 1/2 are really not telling us very much about what is going on in this system. And in particular, you see this large variation with the Prandtl number. In 2D, perhaps there's even a decrease in trend. So we don't really know what is going on. Yes? These simulations, I believe, are for the isothermal case. So both boundaries kept at the same 0 temperature. with the source being the same. So yes. Yes, so these are data for the problem that I've talked about. In fact, for this IH1 case where both boundaries are the same temperature. Yes, thank you for that question. So at least for that case, and one might expect also for the other ones, when the thermal boundary conditions change, we see that the situation is not very well captured by these rigorous results. And so one might expect that perhaps one could decorate these upper bounds at least with some corrections that depend on the Rayleigh number and perhaps also the other governing parameters. And there have been some conjectures. So for example, David, for this insulating bottom plate case, conjectured that the correction should scale as the Rayleigh number to the -1/3, and this is by boundary layer arguments, energy balances, hypotheses that certain quantities scale like other quantities. And one could do the same for the isothermal case. In this case, there's much more variability on what exponent one predicts, depending on what physical assumption one makes. And I'm not saying that one is better than the other, but one could posit different phenomenological theories and therefore see different exponents, right? We would really like to have theorems and rigorous results that tell us what is going on. And so we set off with my collaborators, and in fact, Ali, who should be here in the audience, has been doing quite a lot of work in this, and then Anush Kumar at the University of California, Santa Cruz. They've really been the driving force behind this. And the punchline of this talk would be that it is indeed possible to prove Rayleigh-dependent corrections uniformly in the Prandtl number, but unfortunately, we're nowhere near these conjectured exponents. So in particular, if you fix the Prandtl number to be any finite number, what we can prove are exponentially small correction in the Rayleigh numbers compared to this uniform bound of 1/2, with this algebraic prefactor here that is slightly different depending on the boundary conditions. We do better if we're willing to go to the infinite Prandtl number limit. In this case, we find algebraic scaling, Rayleigh to the -2 and Rayleigh to the -4. But again, we are nowhere near getting these fractional powers that heuristic arguments are predicting. So these results are published, the one of finite Prandtl in this paper with Anush Kumar, Ali, and our collaborators, John Krasky and Andy Wynne at Imperial. That's already on archive and hopefully should appear in JFM soon. The other paper at the infinite Prandtl number, we're still dotting the I's and crossing the T's, but we're hoping to post it on archive quite soon. So for the rest of this talk, I would like to give you a flavor of how one goes and proves these results, because I think the method and the technology requires some subtle analysis, but it's also quite interesting. It's quite general, I believe, for this type of problem. And I would like to focus on this case over here of finite Prandtl number with isothermal boundaries for definiteness. The same strategy applies to all of the other cases, and then depending on how we're doing with time, I will discuss in more or less detail what modifications need to be done in that case. Yes? Okay. Yes. So for the online audience, the question is whether we can look a little bit more about what happens in the heuristic case. So let me go back to that case. So for the case of an insulating bottom boundary, you can make arguments that link how the thermal dissipation goes as opposed to, for example, the mean temperature, and you can start linking these different quantities. And I think David here is the expert in the room about this. And you can make a prediction that the exponent should be -1/3, right? And these again are based on boundary layer arguments, analogies, things that one might expect to see and one sees in simulations, right? The other arguments, we've put them in this paper where we study the isothermal case. And here you can mimic these classical arguments by Malthus, these marginal stability arguments, or the free fall velocity arguments by Spiegel. But because these problems are not symmetric in the vertical coordinate, as opposed to Rayleigh-Bernard, you really have to look at subtle balances between different boundary layers. And so you have to come up with scaling arguments that really look at the difference in contributions to the heat transport that come from the top boundary layer versus the bottom boundary layer. And then you need to add more assumption on how you do that. And for that reason, you could come up, for instance, in the classical regime, right? If you have a marginal boundary layer stability argument, you could come up with an alpha, which is either an 1/8 or a 1/4. depending on exactly how you decide to balance these two boundary layers. And if you look at the analogous of the ultimate regime, so this free fall velocity, where you believe that the boundary layers aren't really limited the heat transport, but you still need to decide how various things balance, and you can come up with either a 1/6 exponent or a 1/3 exponent. I'm not saying that either of these exponents is correct. I'm not saying that one is better than another. They're just assumptions that you could try to make. The point here is it is very difficult. And in fact, there's this recent work by the group in Germany that tries to extend the general theory for Rayleigh-Bernard to the internally heated case. And they do not look at this quantity. And I think it's exactly because it's a very subtle balance between very different boundary layers. And it's not clear what assumptions seem realistic and one should make.
Now you're trying to monitor the product and not the average, but if you relate it to the average, so we should know.
Okay, so the question again is, we're trying to monitor WT. The question is whether we could relate it to the mean of the temperature, for which we have much better results. And the answer here is that's exactly the difference between internally heated convection and Rayleigh-Bernard convection. There is no really any a priori relation between these two quantities that you could derive from energy balances or from the equations. They're fundamentally different quantities and they display different behavior. Rich? Yes, let me just write down the equation. I'm hoping that the online audience will then be able to see this. They can kind of see it, I guess. Yeah, that's actually better. That's a good idea. So we have the temperature derivative plus u dot nabla T equals Laplacian T. This will be the standard heat equation, but now we have a +1. And so this +1 is what makes it hard to relate things between the thermal dissipation and the WT.
Can I make a comment on the way you wrote it? If I would like to make the boundary conditions homogeneous in both cases, the right-hand side here will have the W instead of 1.
The boundary conditions are homogeneous because the thermal boundary conditions are always homogeneous because they're always 0.
No, but I'm saying in the Bernard case.
In the Bernard case, that would be a W.
By W.
Correct.
And this is big difference because 1 is 1 and W will be very large because it is stability. That's the main difference.
Correct. So here for Rayleigh-Bernard,
and now the same boundary condition.
In perturbation form. Oh, sorry. Or even the red one? Shame. Wow, okay. Never mind.
You're trying to hide something.
The details. David has a comment. Perhaps we can, do you want to speak it on the microphone or I can repeat what you're saying?
I don't want to delay too much more. But are you going to explain how the WT relates to the difference between boundaries?
I was not going to do that because it keeps. Correct. The value of 1/2 here, as David points out, is not really anything special, but it depends on the non-dimensionalization. One could relate WT to other quantities that arise that have physical meaning. So for example, let me consider the case of isothermal boundaries. As I said, we're adding heat in the domain, and then the heat has to flow out of the domain if we have a statistically steady regime. And so we can have heat going out of the top and heat going out through the bottom boundary. You do get a WT, but you also get a +1.
Yeah, so when WT is a half, does that mean that you've got half of that heat transport, that are half conducted?
I'm about to say that. So what happens is that a bit of the heat input has to go out to the top and a bit of the heat input comes out to the bottom. And the question is how much of it goes out to the top and how much of it goes out to the bottom. And it turns out that the fraction of heat that escapes through the top is exactly 1/2 plus WT average. And the fraction of heat that comes out at the bottom is 1/2 minus the average of WT. So WT in this case effectively quantifies, at least in the first set of boundary condition, quantifies the asymmetry of the heat flux through the boundaries. And so having a bound which is 1/2 is saying the heat can only go out of the top. And so the physical question and the mathematical difficulty is improving that there is always some amount of residual heat that goes out through the bottom of the boundary. This interpretation doesn't work for the second set of boundary conditions because in this case we have no flux of heat through the bottom. Everything has to go up through the top. But in this case, WT can be related to a Nusselt number. So 1/1 minus 2 WT average is effectively a Nusselt number. And that essentially measures the strength of convection as opposed to conduction. So this is another difference with these internally heated convection problems compared to Rayleigh-Bernard. It's giving physical meaning to these various quantities that one might realistically want to consider is more subtle. And the boundary conditions really play a role. Whereas for the Rayleigh-Bernard convection, one could change the thermal boundary condition and still talk about convective heat flux as opposed to total heat flux and define a Nusselt number in that case. Okay, so if there are no more questions, I think this is nice, but I will try to give you a feeling for how one proves these results. Okay, so let me start by describing a general framework for searching for bounds on mean quantities. And if you were here on Tuesday, maybe you've seen this before because Sergey also explained it, but I'm going to go through it again. So the observation is actually quite simple. Let's suppose that I have a function v that depends on the velocity and the temperature, and that this remains bounded along solutions of the Boussinesq equations with the internal heating. Then if you differentiate this function in time and you take the infinite time average, you discover by the fundamental theorem of calculus, assuming that everything is regular enough to be able to do this calculation, you discover that this infinite time average is 0. So I can take the infinite time average I want to calculate here of WT, and I can add dv by dt under the average sign because I've essentially added 0 cleverly disguised. And then I can take my v, I can take the governing equation, I can calculate an expression for this time derivative, and I'm going to call it LV, right? This is just the Lie derivative of this function along solutions of the Boussinesq equations. So now I have a different quantity that I'm averaging, but it has the same average as what I'm interested in. And at this point, I'm going to make a very simple observation, right? This is a function of time that evolves along a trajectory, which I've sketched here on the right. And it's a trajectory in an infinite dimensional phase space. It goes around, perhaps it is chaotic. But the average value of this function as you go along this trajectory is going to be bounded above by the maximum value along this trajectory, right? Pointwise maximum. Of course, we don't know where this trajectory lives in phase space if we don't want to solve the equations. But if we know that every trajectory eventually enters a certain absorbing set in phase space, then we can extend the maximization from this blue line here from the trajectory to this set, right? And then perhaps we can maximize this quantity here over all velocities and temperatures that now don't need to satisfy the equation, but are inside this set, and this could be a tractable maximization problem, right? So you might think that this approximation by enlarging the set of competing UNTs that we're considering is quite crude, but it turns out that if you choose your function v carefully enough and your equations are well poised and this absorbing set is compact, then you can make this estimate as close as you like to the value that you're trying to estimate. So the method is somehow sharp. Of course, the difficulty is for the Navier-Stokes equation and Boussinesq equation, finding this compact absorbing set. Perhaps in 2D, we know whether these exist, but in 3D, certainly not. And also, in fact, most of the work goes into constructing this function v, right? The strategy doesn't tell us how to construct this and what this should look like. So we could settle for a suboptimal v and find conservative bounds. Even then, it's not clear what one should do. But luckily, Charlie Doering and Peter Constantin 30 years ago told us what to do. right? It turns out that the background method that's been used so successfully in the past 30 years is a particular application of this general strategy. And it boils down to taking a V that has two quadratic terms. The first one is proportional to the kinetic energy of the fluid. And the second one is proportional to the energy of temperature perturbations compared to a Z-dependent background temperature profile, which I'm going to call phi. And you can weight these two terms, give different weight to these two terms, and I'm going to call the weight for the first one beta 1 and beta 2 the weight for the second one. And if you're familiar with the background method, these are the balance parameters. That's the name that they go by. Here, I'm going to assume that this temperature profile here, phi, satisfies the same isothermal boundary conditions of the flow. But to simplify calculations, I'm going to make a change of variables. And instead of working with this phi, I want to work with the function tau. And so I'm going to express the background field in this particular form. That just makes calculations more convenient. It seems like it doesn't, but if you then go through the motions, hopefully I will convince you that it does. And by doing that, now I'm going to tune this function tau, as well as the constants beta 1 and beta 2, subject to these boundary conditions. I've just modified the boundary conditions such that this whole function here vanishes at the top and bottom. Okay, so now that we have our candidate V, you
say that's more or less what I call the available potential energy of that section. So you've got kinetic energy, right?
the available potential energy would be the Z-1 term. Because Z-1 integrated against T, if you expand the square and look at the cross product, that would be the
energy associated with the background state by rearranging your T is unavailable. So the difference is the available potential energy.
Right. Yeah. So one could see these as an available potential energy, but we are free to choose what this background reference state is. And it doesn't have to satisfy the equation. It doesn't have to be a steady state. It's just arbitrary. We could choose it however we like, subject to the boundary conditions and perhaps something else that I will mention in a second. So, okay, so now that we have our candidate V, we can calculate the derivative, we can add it to WT, we can go through the motion. And if you do that, it turns out that you will end up with an expression that has a very nice form. And it is nice in the sense that we have 1/2 popping out here, which is going to be the eventual asymptote. And then we have some terms that depend linearly on the temperature, in fact, on its vertical derivative, and then some quadratic terms. Right now, if you remember, I said that we would like to maximize this expression over here. So if we can choose our tau, our beta 1, and a beta 2, such that these quadratic terms are positive for all w's and t's over which we want to maximize, this means that this quadratic function is somehow like a concave parabola in an infinite dimensional space. And so it will have a finite maximum. And this will give us a finite upper bound on this quantity here on the left-hand side, and therefore on the mean of WT. To do this, we need to define the set of admissible velocities and temperatures. And we know that these are better satisfy boundary conditions and incompressibility. But we also have another crucial bit of information, which is a minimum principle for the temperature. So at long times, one can prove that the temperature field in the Boussinesq equation with internal heating has to become non-negative pointwise, at least almost everywhere in the domain at large times. And this is a consequence of the fact that we're really heating the fluid. So any negative temperature initially has to rise because we're only cooling through the boundaries. And so one can enforce this pointwise constraint using standard Lagrange multiplier techniques. I don't want to go through the details because the calculation is like 2.5 pages long. But effectively, the signature of this constraint will appear through what I will call a Lagrange multiplier lambda of the vertical coordinate that will appear in the next slide. So every time you see a lambda, that arises because of this constraint, and it will be essential to have this information into our problem. So having defined this set of admissible temperatures and velocities, we can maximize this quadratic form over here, provided that we have chosen the variables in blue here, tau, beta 1, and beta 2, to make these quadratic terms positive. And the result is this one, is this upper bound here. The mean of WT is bounded by a horrible expression that I will dissect in a moment. But we have conditions on this, right? We're not free to choose these variables as we like. We have the boundary conditions on tau. We have some conditions on this function lambda, which are effectively telling us that it's acting as a Lagrange multiplier. They come out of the analysis. The details are technical. I don't want to go into them. And then the last constraint is that these quadratic terms need to be positive. Okay, yes?
So are you doing the quadratic terms because you believe the linear term will not contribute to the symmetric?
So correct. So it's a linear term. It's like having a parabola. So the quadratic term is telling me that the parabola is concave, and then if you add a linear term to this parabola, it will still be concave and it will decrease at infinity as a quadratic function.
That term which is got 1 power of e may not be a linear function because of the asymmetry.
Correct. So the temperature itself will not be linear. The temperature that maximizes that is definitely not going to be a linear temperature, but it doesn't affect the argument. The only way in which it enters is in the form of this horrible expression over here. So having that linear term, if I didn't have that linear term, this would be positive. I plug in 0, I get 0. That would be the maximum, and I would just get a 1/2. Because I have that linear term in that expression, I pick up all of the rest here, and I'm just going to describe it in a minute. So if you're familiar with the background method, this is a kind of problem that sort of arises, and you could see what you would like to do. But the goal here is, I will repeat, choose this function tau, this Lagrange multiplier lambda, and the constants beta2 and beta1 that satisfy all of these constraints and make this expression as small as possible, possibly less than 1/2. So let me try and dissect these expressions. So we have 1/2, which is going to be the eventual asymptote. The rest of the terms will give a Rayleigh dependent correction. Of these terms, one is nice, right? If we choose tau to be a positive function, then we have 1/2 minus something positive, which is good. But the second term is bad because it's the integral of a square. So it's an L2 norm type of term. And so you immediately see a competition between the term in green and the term in red. And so there's a subtle balance in how one chooses this function tau, lambda, and the constants, even just at the level of trying to make this function, this whole expression, be less than 1/2, forgetting all of the constraints. In terms of the constraints, there's a competition also here for the quadratic form. We have some nice terms if beta1 and beta2 are positive, but we have a term which is not sign definite. And so if we want this expression to be small, we need to dominate this term highlighted in red using the other two, and so we better make this small. Now W and T vanish at the boundary, so near the boundaries this is fine, but in the bulk of the layer we don't have any control on W and T, and therefore we should probably take tau prime be equal or at least very close to beta1. So if beta1 is a positive quantity here, we expect tau to increase almost linearly throughout the domain. But this is incompatible with the boundary conditions because we need to go from 1 on the left to 0 on the right, or at the top and the bottom. And so as a function of z, tau on average needs to decrease. So you might expect some boundary layers to accommodate this type of boundary conditions, but then we have tau prime. And so if you have boundary layers, you need to start worrying about tau prime here in the cost, because maybe you have large derivatives in boundary layers, and this term here becomes large, right? And then that's where this Lagrange multiplier comes into play. So there's a lot of subtle balances in this problem. It's not obvious how one might construct these functions. There's a lot of freedom in how one might choose the boundary layer structures. So how should we do it? Well, I'm not that clever, but I like to ask computers to tell me what the answer is. So there's nice ways to solve this problem computationally and try to minimize these expressions subject to all of the constraints. And if you do so, I could give a whole talk on how this is done. But if you do so, you find this black line over here. And you immediately see two things. It's an upper bound on the data, not a very good one, but that's okay. We settle for upper bounds. And also you see that very quickly as the Rayleigh number is increased, this line increases and approaches 1/2. Now it looks like there's a sharp corner, but it's not. So let me zoom into this small region over here highlighted in red. And if you look closely at that region, you see that it's a very fast approach of this black line asymptotically to 1/2 from below. And the corrections here are really small, which are sort of numerically challenging. So it's quite hard to push the computations to very high Rayleigh numbers and estimate what the decay rate here it is. If you try and fit a power law or a straight line, you find something like Rayleigh to the -40 or -50, so a very rapid decrease. But that's not perhaps the most important part of the calculation. What we gather from this is that it should really be possible to construct these functions and constant to get a bound which is strictly less than 1/2 at every Rayleigh number. How do we do that? Well, we better look at these tau functions and the lambda. So here I'm plotting this tau over the full domain in the middle panel, and you see this sort of S-shaped structure where we have a linear increase as we might have anticipated, and the slope here is exactly that beta1 constant. We have boundary layers, one near z = 1, which is quite simple. In fact, you could approximate it with a linear function, and we will do that later. But if you zoom in near z equals 0, you find a very, very interesting structure where you have a boundary layer with inner sublayers, which are separated by sharp corners. So this function is actually not smooth. And so this is plotted in logarithmic coordinates. Otherwise, you wouldn't see anything. But I'd ask you to believe me that the first part here, we start at 1, and then we decrease, in fact, linearly in this inner sublayer. And then we have a very precise 1/z profile here. You could actually see it very well if you plotted it in a log. This is a linear log scale, but it's a 1/z profile in this outer boundary layer. And this type of structure, I wouldn't have predicted if I had to think about that problem myself, but the computer is telling us that this is the structure really nicely. On the other hand, we see this function lambda, and this is almost piecewise defined. We also have a boundary layer here. This is all enlarged near z equals 0 because the scale is logarithmic. So we have a region where this lambda is constant, a region where it increases as 1/z squared. And then for the rest of the domain, this is a squished layer, but it's in fact the majority of the domain because the coordinates are logarithmic. Then we have a constant function here. And now if you look at this close enough and you can try to do quantitative comparisons, you observe that this lambda in fact matches the derivative of the function tau near 0, and in particular in this boundary layer. And this can be understood by looking at the expression of the cost, the bound that we're trying to minimize. In this boundary layer, tau prime is really large, so the bad term would be very large. So we have to use this function lambda to try and counteract it. So that's the whole game that we would like to play, right? And so the challenge for the analysis is to try and replicate this behavior analytically and estimate the various terms so that we can win and find an upper bound on the mean vertical heat transport that approaches a half from below. So this lambda, the question is, what is the lambda? This lambda is a Lagrange multiplier for the minimum principal on the temperature, right? So there are technicalities in there in the conditions that you had to satisfy. I will remind you there's 2 conditions. It has to integrate to -1. That's fine. It's just a normalization condition. The other condition, which is more important, is it cannot decrease. It has to be a non-decreasing function of z, and you see that here that it is indeed true, right? It can only go up or remain constant. So that's an important condition for the analysis. But you see that if we didn't have it, then we wouldn't be able to control this term. And that's why imposing this minimum principle is really vital for this internally heated problem. You didn't have to do it for Rayleigh-Bernard. Perhaps you don't have to do it for the internal if you look at the mean temperature, but if you look at the mean of WT, then you really have to use this information. Otherwise, you're not able to control this term. And in fact, then you find that this expression will blow up as Rayleigh goes to infinity. So anyway, we then try to sit down and replicate this by hand. And it turns out that one can. So we can take profiles that look a little bit like this. So we have a boundary layer near z equals 0 with 2 parts, an inner boundary layer with linear decay, a region with a 1/z profile, and then a linear increase and a linear decrease. And we can take the corresponding lambda to cancel exactly the derivative tau prime in this boundary layer near 0, and then be 0 identically everywhere else. So if you take these kind of profile, and this is really the work and insight of Anuj, who looked at the numerics and came up with these, you plug these profiles into the expression, and the bound on WT becomes a half minus something, which is sigma delta log of 1/sigma. Here, sigma is the relative widths of the inner and outer boundary layers near the bottom of the domain. Here, z equals 0, plus some positive terms that depend on all of the other constants that we are free to tune. And these are going to tell us the widths of the boundary layers near the bottom, near the top, the positive term, the amplitude of the positive term here, the slope of the profiling here. Of course, we need to choose these parameters to satisfy this positivity of the quadratic form constraint. And the key ingredient here is to use an estimate, which is of Hardy-Wellich type, which is a weighted estimate that gives us control on a term which is WT over Z square effectively, in terms of the gradient of U and the gradient of T square. So without this estimate, you can't really control those terms that come from this boundary layer here in the constraint. But if you use it, you can, and you discover that the best thing you can do is make this positive term here in red scale as sigma times delta times Rayleigh to the 3/5. So now if you want the green term here, sigma delta log of 1/sigma, dominate the bad term, you'd better take sigma to decrease exponentially so that you can eat up the negative terms, and that's where the exponential bound comes from. So if you follow through the algebra, you end up with the bound that I stated at the beginning, which has this exponentially small correction in the Rayleigh number, and that's why it's a Rayleigh to the 3/5. In the process, you pick up this sigma delta, which gives you a Rayleigh to the 1/5 as well. So I think we have about 10 minutes left, and then so I will very quickly give you a flavor for the other cases. So far, I've focused on this top left case. I would very quickly give you an intuition for how you go and prove the other ones. So let's start with the case in which the bottom plate is insulating, but the Prandtl number is still finite. In this case, I can go through the motions, same type of bounding framework, but the problem for the upper bound is slightly different. And in particular, we have different conditions on tau and on lambda. We don't have a boundary condition on tau at 0, so we don't have to have it start from 1. So we have that freedom. But at the same time, we are not free to choose this lambda to be very large and negative to cancel large derivatives of tau because we have it limited to -1. The other constraint is the same, but we can play the same sort of ideas. And so we can try to dominate this bad guy here by trying to cancel these two near z equals 0. And so the strategy here would be to choose something that looks quite similar to what we have, but we limit lambda to be -1, which means that the slope here on the left of tau is limited to -1. And you can do the same type of estimates, and you end up with a bound that looks almost the same, except this Rayleigh to the 1/5 becomes a Rayleigh to the -1/5. And that's just a difference in the fact that we can't have this profile shoot back to 1, and that's where that -1/5, I believe, comes from. Slightly more interesting is the infinite Prandtl number case. So I will focus on the case of the isothermal boundaries here. In this case, the equations of motion simplify because all of these terms that are multiplied by 1/Prandtl drop out. So the nonlinearity in the momentum equation drops out, and you can effectively slave the velocity to the temperature, which becomes the only dynamical variable in the problem. And in particular, you have this bi-Laplacian equation that links the vertical velocity W to the temperature. Right, so we have much more control onto this product WT now, and we can play the same game. This time, this function V is just the energy of temperature perturbations. We don't need to consider explicitly the velocity because we have explicit slaving in terms of the temperature, but we can play the same game, and you can formulate a bounding problem that looks almost the same as what we had before, again, with the conditions where the integral of lambda was -1 and it had to be a non-decreasing function. But this time, what changes is the quadratic form that needs to be non-negative. And here, I've just written W explicitly in terms of T. We have a slightly simpler expression that we need to dominate. But again, we have this term, which a priori is not sign definite, so it needs to be dominated. And here, I will use a result by Doering, Otto, and Vesnikov, which was derived for Rayleigh-Bernard convection, but actually is a result about the bi-Laplacian equation linking W and T. And it says that if I were to choose tau prime to be 1/z plus 1/1 minus z, so this means that tau is somehow a logarithmic function, then this sign indefinite term, when W is given by the right function of the temperature, is actually positive. So this term here, which is a priori indefinite, if I chose my tau to be this logarithmic function, is actually positive, and so I don't have to worry about it. Of course, I can't do this because this derivative here of tau prime would be positive, and I can't satisfy the boundary conditions, but then I can introduce boundary layers, and I can play the same game that was proved for the Rayleigh-Bernard case. So I can do this. Here you see this sort of logarithmic profile in the bulk of the layer, which is going to give me some positive contribution in that quadratic form. Linear boundary layers, in this case, I don't need this fancy 1/z structure and this sublayer structure, which was much more subtle in the finite Prandtl case. It's much easier to control the contribution of these boundary layers. We have freedom to play on the amplitude of this point here, so this A, but you can do the analysis and you can figure out how these things should scale, and you find a bound on the mean vertical heat transport that has this algebraic scaling. Quite interestingly, the first thing that we tried to do to simplify the algebra was to choose the bottom boundary layer with delta and the width epsilon of the top boundary layer to be the same. But the problem is inherently asymmetric. And if you do that, you lose some freedom and you pick up an extra load. So having this freedom to tune the boundary layers independently is actually quite important in this case to optimize the bound and get some extra, a clean power law scaling. So the final thing I would like to do, and then perhaps we can go for lunch, is give you tell you what changes when the boundary at the bottom of the domain is insulating. And in this case, we pick up again this constraint that the lambda function has to be constrained by -1. So the slope in tau of the boundary layer has to be -1. We can't have a steep boundary layer. And that's the main reason why we have a different power. There are slight complications in the shape that you need to take here in the bulk of the layer for tau. The main one is that the 1/z needs to be changed to 1/z to the alpha for some alpha between 0.5 and 1. But this is the technicality, and you can use extensions of this result by Doering, Otto, and Reznikov, which was proven by Whitehead and Wittenberg. It's quite technical, but the analysis goes through, and one can prove positivity of that quadratic form and go through and establish the result. So I think this is enough technical stuff for the talk. So I want to leave you with a summary of the 4 bounds that I've discussed, but I want to summarize a few takeaway points. The first one is that bounding the mean of WT, this vertical heat transport for internally heated convection, is significantly harder than bounding the mean temperature. One is related to the viscous dissipation, one is related to the thermal dissipation. These quantities in internally heated convection are different, and one is much harder to study than the other. The minimum principle on the temperature for studying WT is absolutely essential. It wasn't used for the bounds I discussed at the beginning on the mean temperature, but in order to obtain anything for the heat transport, we absolutely had to use it. And if not, we wouldn't be able to even obtain a uniform bound of 1/2. We would find something that explodes as Rayleigh goes to infinity. The way in which these bounds are derived, aside from the technicalities, I think is quite interesting, because we have this modern, I would like to say, formulation of the background method, which makes it very systematic, very flexible. We can start to add constraints like this minimum principle on the temperature, but you could even start to derive conditional bounds. You could say, well, if my temperature satisfies these conditions, then I would obtain a bound that behaves in this way. So you can start to play around with the framework and start to probe this bounding framework and the system that you would like to try and see what you would have to prove in order to be able to achieve a certain result. And then a side point is that computations and try to implement this bounding framework computationally is actually quite revealing. And it was a key enabler for the analysis in this case, because it revealed this fine boundary layer structure, which I would never have come up with myself. Maybe someone cleverer than me would have, but I would not have done that. There are, of course, some open questions. We don't know if any of these bounds are really optimal in terms of their scaling and the powers that you see. We don't know if they are sharp. Are there solutions to the Boussinesq equations that display this type of scaling? Perhaps it doesn't seem very likely to have exponentially decaying approach to heat transport that is 1/2, but I don't know. If they are not sharp, how can we improve the bounds? I think new ideas here are needed. I don't see how one could get much more out of the background method approach that I've used. Then I don't see how these results could be refined. But again, I don't know. Perhaps there's some insight that one of you might have, and I would be happy to discuss that. More generally, these results are nowhere near what you see in the data. So what is going on, and can we say anything about that? So with that, I will stop here. Thank you for your attention.
Thank you for a beautiful talk. Since we already had quite a few questions from the audience, I'm going to give the online participants maybe a chance to ask some questions. Are there any questions in the chat right now? Okay, online participants, if you have a question, please unmute and ask your question. Okay, well then we can go back to our audience in person here. I'm going to bring you the microphone.
So out of curiosity, I've seen the picture you drew about on the tau, and I always noticed that you were careful in drawing the lambda boundary layer pretty large compared to the epsilon boundary layer. So the bottom boundary layer has always been.
You mean
Yeah.
in this type of picture?
Yeah, exactly.
So okay, this is just a sketch. I haven't drawn the
Yeah, but that
the
was
preface to scale. What tends to happen, at least for the this is a sketch for the infinite Prandtl case. In this case, you discover that the bottom boundary layer is thicker than the top boundary layer. In fact, in the analysis, we don't really need to specify what this is. We get a range of possible values, and that's because the estimates that we make on these bound, we do them to leading order, and they only depend on delta. If you were to do finer calculations and really optimize, then you could see exactly what this is, but it will be smaller than the bottom boundary layer. I don't remember how the situation is for the finite Prandtl case, but perhaps Ali can comment on that if you remember.
For the finite, there was nothing to do with the case.
But do you remember which boundary was thicker? Which boundary layer was thicker?
In the finite case, they were equal.
Okay,
And
right, in the
in this
finite,
one,
the
the-
finite Prandtl number case, the delta and the epsilon are actually equal.
But just to be clear, in this one, delta is smaller than epsilon. Yeah,
Is it?
so delta is thinner than what epsilon could be.
Right. Okay.
Yeah.
Ali is the one who's
And
done the
delta is
calculation
the
in
thing
detail,
that's
so I will
constraining the
believe
bound.
what he says.
Some more questions in the back. Okay.
Hi, thanks for a very, very nice talk. So my question really is here because I've been playing around with equations. This is basically a constant heat flux going in, right? And it's just a question of which boundary the flow prefers.
Correct.
And essentially the fluid is trying to turn off the heat flux going downwards.
Correct.
Now, is
As
there
far
any-
as the bounds are concerned.
Yeah, yeah. And I guess that's what people find in numerics too. I mean, I don't know.
To a point, yes. I'm not aware of any numerics at infinite Prandtl number, but the finite Prandtl number, the question is the same. And how do I go back to the?
I mean, my question was really, how does
Yeah,
this system relate to a constant heat flux convective system? So, I mean, in terms of these scalings that you're getting out for your bounds, could I recognize, could I convert one of these quantities to something in the constant heat flux Rayleigh-Bernard problem?
Not that I am aware of. That
In the bottom row.
kind of in the bottom row,
Yeah,
because in this case I can define a Nusselt number,
yeah,
just as by taking the inverse of these bounds and taking the minus. So
yeah,
you could take a half minus WT
yeah.
and then inverse that, and you would get a Nusselt number.
Yeah, that's what I was playing
But
with at the
it's-
back, but
It's
it's not
not
it's not quite-
comparable in terms of the scaling, at
Yeah.
least for what we can prove. I don't know about the simulations.
right.
There's
I'm
not
just,
much data that is available.
yeah, I'm
and
just wondering if those problems are related in a way that's not immediately obvious, because of course they're both constant heat flux problems, and you're letting the fluid decide how it's going to get rid of that flux.
It is a very interesting question. I agree. We've thought about it briefly, but it's definitely not obvious how these two systems are related. One might even start to play with concentrating the heat towards the bottom boundary and have non-uniform heating, for example. It's unclear whether taking any limits of how the heat is
Yeah.
distributed, whether one fixes it through the boundary at the bottom and then at the top to have an outwards flux. I'm not aware of any results that say that one system collapses into the other. I don't know if perhaps David has comments on that, or someone who knows about the analysis of these equations more
thank
than
you.
me will be able to comment on that.
Yeah, concerning your last couple of transparencies, when you have bilaplacian on W,
Yes.
then you'll talk about bilaplacian inverse.
Yes.
What boundary conditions you have?
Aha. So correct. That's a very good question. I've brushed this all under the carpet.
Of course.
So you have non-slip
This is your
boundary
job.
condition. Yes.
No, it's okay.
Here the important boundary conditions are the non-slip ones, and then you can combine them with the incompressibility condition to also find Neumann boundary conditions. So it's sort of H20 type boundary conditions for the velocity W at the top and the bottom. So both W and their vertical derivatives vanish.
Aha, good.
Sorry. Where is that?
Okay.
So here W
So use the incompressibility
correct.
to deduce
to deduce this
Neumann on the W.
correct. Absolutely correct. And these boundary conditions are actually fundamental for the estimates and the results by Doering, Otto-Reznikov, and then the extensions. They absolutely rely on those boundary conditions.
Yes. Thanks.
There might be something that one could do if one had free-slip boundary conditions, because in that case, at least in 2D, one could use vorticity, which has been done before. But we've started to look at that. I think Ali has a preliminary result on that, but I don't think we're quite ready to discuss it publicly. At least we can discuss in a separate room.
Rich wants to make another comment.
Yeah, I'm just an idea came to me. So you don't have to have uniform heating here, do you?
Correct.
You you could pose the question, you know, what heating profile could I have to do something optimally? Have you thought about that?
We have started to think about non-uniform internal heating. The problem is that depending on what the heating profile is, one may or may not have this minimum principle on the temperature. So
Yeah.
that's one potential issue. But we've started to look at that. There are some preliminary results that we have, but again, we haven't really explored in too much
Right.
detail what the effects of the shape of the heating profile is. But it's certainly possible to extend at least some of these results.
Because
to the
there's a paper by
non-uniform
Buser,
case.
isn't there, where he does it in spherical geometry, motivated by the Earth's outer core. Have you seen that paper?
I am not aware of this result, but perhaps you could send it
Yeah.
to me.
Okay.
Okay, one more chance for the people online to speak up. If not, then Idris has another comment.
I have a question concerning the construction of tau that you have here.
Right.
Did you construct it by kind of guessing, or did you have something kind of more fancy for constructing it? Because I took like 1/1z minus something like that.
So that's the insight that came from, I think, was it Camila? Can you confirm that was Felix Otto's idea of having this logarithmic profile for the infinite Prandtl number case? So we had experience for the Rayleigh-Bernard problems where that kind of construction had worked. And so it was just a question of having that as inspiration and transferring the estimates to these internally heated cases.
So it's like inspired by the.
It is inspired by the Rayleigh-Bernard.
But what
case.
Otto came, which is inspired what did Nikolaenko, Scherer, and Timam, and
Yes, yeah.
and
So it goes back quite a
Poulet,
long way.
Ekman, and the company.
Sorry. So that if the question was about the infinite Prandtl number, then we had the previous experience. For the finite Prandtl number, we actually computed this optimal tau numerically. And this is where this fine boundary layer structure came out of. And I could not have guessed, at least I personally couldn't have guessed that structure just by looking at the problem without having the calculation. I think that's why the numerics and being able to implement these problems computationally is quite a valuable tool.
Very nice. Thank you. Very nice.
No problem.
Okay, let's thank the speaker again.